Hello, and welcome to our next demonstration of the Oz Optics DSTS measurement system. In today's demonstration, we are going to show you how the DSTS unit can be used to detect the development of cracks in structures such as dams, pipelines, or roadways. This is one of the most important applications for the DSTS unit. Many people asked us how it is possible to detect such spine events, which are only fractions of a millimeter in size, given that the instrument is specified as a minimum spatial resolution of 10 centimeters. Well, in today's demonstration, we're going to show you how it is possible to see those events, even with that resolution specification. To demonstrate that, we've set up our instrument together with a reel of 750 meters of fiber, which is then connected to this fiber that we've put onto this plate to simulate our structure. It then goes back to another reel of about 200 meters of fiber and back into the instrument. This will form our test bed for our experiment. Let's talk about the structure here in more detail. So here we have our experimental setup to demonstrate detection of the formation of cracks within a structure, such as a road or a dam and so forth. We have a sheet of plastic here to which we have bonded an optical fiber around in a series of 5 loops. 1, 2, 3, 4, 5, in a manner similar to what someone would apply a fiber into a structure. We have made a cut into this sheet to which we are going to insert a wedge to expand and contract the cut, simulating the formation of a crack within a structure. We will demonstrate how you can detect the expansion of this gap, as 5 separate events along the fiber. Let's start the test. So let's set up the instrument to make our measurements. We're going to pick BOTDA for making the measurements. And let's talk about our setups. We've set the fiber length to be 1,000 meters long, slightly longer than what our actual setup is. Our pulse width is set up as 1 nanosecond. With 1 nanosecond pulse, the spatial resolution from our pulse is 10 centimeters. Our spatial step size for our recording is 0.05 meters. Again, half the size of our actual pulse width through the fiber. We have our averaging set at 20,000 samples. We've set it at a nice high number here, so we're able to get a good reliable reading. This is standard Corning SMS 28 fiber, widely used, commercially available. And again, we're using our fast general analysis setting here for making the measurement. So as usual, we start off by making our baseline reading. So we click on measurement, we hit baseline, and we hit the start button for the laser scan. We're going to save this as a new baseline readout. Again, the important thing here is to get off an initial baseline reading that shows the initial state of the fiber. Once we have that baseline reading, we are then going to insert a wedge into our plastic sheet here to simulate the development of a crack. And we'll show how that change induced by that crack development shows up as a variation compared to our baseline reading. Okay? So it's gathered the data, it's now doing the analysis, and this will give us our initial baseline reading to start from. Once it's up, here's our baseline reading. This is our initial 750 meters of fiber, and at this point here we have the transition to the other fiber. And in between here in this section is where we're going to see the development of the crack. So let's take an initial measurement of this before we actually start causing a crack to develop and expand here. So we're going to select on strain temperature. We're going to make sure that relative strain is clicked on, and we start making our measurement. Okay, so it's finishing the analysis. Sorry, it's finished gathering the data and now doing the analysis. And of course, we start off here with a very flat curve. We can zoom in to an area. We can zoom in to an area. And it looks quite flat and uniform across the surface, as it should. So let's now start simulating the development of a crack in our setup. Alright, so to begin, let's measure the initial width of our gap in our plastic sheet here, and then widen it and show the difference. So, using a pair of calipers, we're making an initial reading, and it's reading 1.34 millimeters in width right now. So to widen the gap, we're using a screwdriver for our wedge. And we're going to gently tap that in to widen our gap. Now let's measure how wide our gap is. And our gap now is 1.55 millimeters in size. So we've made it 0.2 millimeters wider than it was originally. And now that we have our wedge installed, let's repeat the measurement with the instrument. So we're just going to start the instrument off, and it's going to begin recording data. So it's just about finished gathering and analyzing the data. It's now done. So if we look along the length of the fiber, we'll notice a definite peak right here along the system. And if we zoom in on that location, we can discover quite quickly that we have 1, 2, 3, 4, 5 discrete events here shown onto the screen. The spacing of these events is roughly half a meter apart. As you can see, we went from 179.42 meters here to 179.88 meters here and 130.34 meters here. So each event here is roughly 0.4 to 0.5 meters apart, corresponding to the distance between points where the fiber crosses our gap in our system. So even though we've induced changes in a section that's less than a millimeter wide, and even though our spatial resolution is set to 10 centimeters, these events are quite obvious on the instrument. And this is what makes the DSTS instrument such a valuable tool for monitoring, for detecting the development of cracks within a structure, such as a dam, a bridge, or roadway. We hope you've enjoyed our demonstration, and we look forward to working with you in the future.